I challenge you to watch the entire video because I guarantee you will learn something. I do not have multiple carbureted engines, 4-strokes, EFIs, a Verado, a 3.3, a 4.2, an XTO, an HPDI, an Optimax, so I can't take 20 fuel systems apart, so there will be quite a bit of talking and diagrams, but I want to start with carbureted engines first because carbureted is going to be the most simple one because the fuel is going to come into the engine like this and it's going to go to a strainer. Then it's going to come out of the strainer and it's going to go to a fuel pump. And then from the fuel pump, it is going to go to a distribution thing that's going to go to the carburetors. Once it gets to the carburetors, then it's just going to go through the carburetors. It's going to get delivered to the engine, through the reeds, into the crankcase, and then normal 2-stroke operation where it goes through the ports into the cylinders. And that is how the system is going to work. Now, there are 2 different common types of mechanical fuel pumps that operate on carbureted engines. Whether that be a carbureted 2-stroke or a carbureted 4-stroke, usually that is the difference between the 2 pumps. Carbureted 2-strokes usually operate a diaphragm pump off of the pulse created by the crank. So as the pistons go up and down inside the crankcase, there is a vacuum, and that vacuum creates a pulse. And that pulse is what operates that diaphragm on the mechanical fuel pump. So as the crank spins around, it creates a pulse of vacuum, and that moves the diaphragm in and out on the fuel pump, which then sucks the fuel from the tank to the engine. And that is why on a lot of 2-strokes, if the diaphragm ruptures in the fuel pump, it will feed fuel into the crankcase, which will make the engine run away or have a very, very high RPM just when it's running because it's just dumping fuel into the engine. Or at the same time, sometimes it won't even start because it is flooding the engine and it can't even run because it's got so much fuel in it. But if you want to know more about the fuel system from the boat to the engine, that was last video. I'll link that one. But the other pump being on the carbureted 4-strokes, most of those are going to be run off of like a dowel basically. So there's going to be a pin that runs off of a lobe that is usually on one of the camshafts. And as the cam spins around, that lobe is going to hit that little dowel, and the dowel is what's going to be able to push the diaphragm on the fuel pump that is going to create that pulse that sucks the fuel from the boat to the engine and feeds it into the fuel system. And this is going to roll us into the electronic fuel injection systems, or EFI. Most common on most 4-stroke outboards like a Verado or just a common V6, V8, 4.2, 3.3, Honda, Suzuki, doesn't matter. An EFI is an EFI. It utilizes different components, but some of them will also utilize that same type of mechanical fuel pump, which will feed fuel to the VST. Now, the VST is a vapor separator tank. Now, let's talk about the entire system before we break down each component within the system. So we're going to have a very similar type of system with the EFI based on the same type that we had here. And that is going to be because the fuel is going to come into the engine and it is going to hit that same thing, being a strainer or a filter. Then it is going to go to a fuel pump. The fuel pump could be either mechanical or it could be electric. Different models are going to have different types, and this pump is going to be called a low pressure pump. So it's either mechanical or it is electric, but either way it is a low pressure fuel pump. Then it is going to go to a high pressure pump. Which is the same thing, it's a fuel pump. And then from that it is going to go to a fuel rail, where you have injectors. And these injectors are going to be run by the computer that tell them when to open and when to close. And the fuel pressure is going to be maintained by something right here, which is a regulator. And the regulator is what regulates the fuel pressure created from the high pressure pump to feed these injectors. Now, these two fuel pumps, where they are and how they are housed, are going to vary by the model. Mercury is going to use an FSM. They also utilize a VST, and pretty much everybody else uses a VST, which is a vapor separator tank. Let's talk about those real quick. So the two different kinds are going to be an FSM or a VST. FSM stands for Fuel Supply Module. VST stands for Vapor Separator Tank. Both of these are going to vary depending on the model that you have. Some of them will have that low pressure fuel pump built into it, but the FSM will always have the low fuel pressure and the high pressure fuel pump built into it. So for our FSM, this is going to house multiple different things. You're going to have a low pressure fuel pump. You're going to have a high pressure fuel pump. But you will also have the pressure regulator. And then you will also have tubes in here that run through the whole thing that are going to have water in them, and these are the fuel coolers. Fuel coolers. So you're going to have the low pressure pump, which sucks the fuel from the tank. It's going to go through that same filter as the other models. It's going to pull that into here. It is then going to fill this FSM full of fuel. Once the FSM is full of fuel, it will then take this high pressure pump that will send that fuel through the pressure regulator and then out to the injectors. And that is what is going to operate most fuel systems on a Mercury outboard. So once it gets to the injectors, again, those are computer controlled, and we'll talk about those in a little bit. But this is the basis for a Mercury outboard fuel system. Low pressure pump, fuel coolers that cool the fuel that is inside the FSM, and then a high pressure pump that then pressurizes the fuel, sends it through a regulator that then regulates that amount of pressure, and then that is what goes to the fuel injectors. Then we are going to have the VST. VST is going to be very similar to the system, but it may or may not have the low pressure fuel pump built into it. It will definitely have a high pressure pump. So the low pressure pump may or may not be in here. The low fuel pressure pump may or may not be inside the VST. It's like 50-50 on some models having it and some models it being external. It is most of the time going to be an electric fuel pump when it is on larger outboards like a 3.3 or a 4.2 or something like that. Once you get down to like a 150, 119, 115, a 90, 75, stuff like that, a lot of times it is still a mechanical fuel pump. So based on the horsepower is going to vary on where this low pressure pump is and whether or not it is electric or mechanical. But once the fuel goes into the VST, it's going to fill the VST up. It is a vapor separator tank, and the tank is going to fill up with fuel. And there's going to be a float in here. This float is going to go to a vent, and that vent is going to vary depending on the model, because some of them is going to vent just straight out. Some of them come underneath, like on a Yamaha. Some of them will come out the handle. Some will be in the front of the engine. Some of them will go through a filter. Some of them will go into a recirculation type of system that recirculates the fuel if it fills up inside this. That float is there to kind of help stop that whole system and like stop this thing from filling up. But it is going to vary in operation based on model, horsepower, brand, manufacturer, etc. We're not going to go much into the vent and the whole vent system. For right now, we're just talking about fuel flow and where the fuel is going to go and how it's delivered to the engine. So in this VST, it's going to have the same thing. Most of them are going to have a pressure regulator. That regulator is going to do exactly what it did on all the other ones. It is going to regulate the fuel pressure that is coming out of the high pressure pump, and then that fuel on different models of the VST is then going to leave that, and it is going to go to a fuel cooler. That fuel cooler could be its own component, or it could be built into the fuel rail. That is always going to depend on the model and all that kind of stuff. And then once it gets out of that, it's going to go to the injectors, and the injectors will then feed that to the engine. So a couple of key takeaways to the FSM and the VST systems on an EFI and the different components. One, they're all going to have that filter or strainer, so the fuel coming from the boat to the engine is going to go through the same type of filter as it did on the carbureted 4-strokes. That's just going to vary. It's a filter. Then it is going to go through a low pressure pump. The low pressure pump is going to be what pulls the fuel from the tank and feeds it to the VST or the FSM. Now the FSM has that pump built into it, and again, the different models, horsepower and brand and all that is going to vary whether that low pressure pump is mechanical or electric. When it comes to the electric low pressure fuel pumps, these pumps are going to be controlled by the computer. Most of them are going to run all the time. So whenever the engine's key is on, that low pressure pump is turned on, and in just the key on position, most of them will operate that low pressure pump for like 15, 20 seconds, something like that. It will depend on the model and the brand manufacturer. But when you turn the key to the on position, that low pressure pump turns on, pulls fuel from the fuel tank, and then feeds that to the VST or the FSM. And that is to just fill that thing up with fuel. Now that pump will turn off if the engine is not started. So if you leave the key on, it's not just going to operate that pump all the time. So if you're trying to diagnose it, then that is something to think about, that key on, it's only going to operate for maybe even 5 seconds depending on the model. So you need to be watching it as far as being power fed to it, because that power is controlled by the computer that's on the engine. So it's not going to have constant voltage there, and you might misdiagnose something if you're looking for constant voltage, because it's not going to have that. Once the engine is running though, and you hit the engine to start, that pump is going to run all the time, because it always has to keep fuel in the VST and the FSM. But once that fuel is into the FSM or the VST, then the high pressure pump is going to take over. So on FSMs, which is Mercury only, all the other ones use basically a VST. The FSM has a fuel cooler built into it. So there are tubes inside the FSM that run water through them all the time, and that cools the fuel. Whereas a lot of the other ones that have a VST, the fuel cooler is external. So it'll be something else after the fact. But again, from tank to engine, we've got filter, low pressure pump, tank. FSM, VST doesn't matter. And then inside that tank is your high pressure pump. The high pressure pump is going to create pressure. Now that pump is only going to operate when you run the engine. Again, at startup, some brands, it will turn on for 5 seconds and then it will shut itself off and wait. It is just there to build fuel pressure at the rail, so when you try and start the engine, it has fuel pressure to operate. That fuel pressure is going to be regulated by the fuel pressure regulator. Most of the time is built into the FSM and the VST. There are some models that have another regulator built onto the fuel rail, so it will vary on where that regulator is, but the regulator is always in between the fuel rail and the high pressure pump. So that way it can regulate the pressure of fuel going to the injectors. And that is very, very important, because if it has too much pressure, it's going to be putting in more fuel into the engine than it wants to, or if it doesn't have enough pressure, it's not going to put enough fuel into the engine, and you could have all kinds of problems, from a running issue to a loss of wide open throttle, or many other different issues based on improper fuel pressure. So some of the models might have that fuel cooler built into the fuel rail. It might be separate, but somewhere between the high pressure pump and the injectors is the fuel cooler and the regulator. Once the fuel is at the rail, that is where the injectors are. The injectors are what allows the fuel to get put into the engine. They are controlled by the computer of the engine, and they have what is called an injector pulse width. That pulse width is basically how long the injector stays open. So if that injector stays open for 1 millisecond, it's just boom, boom, open, close. It's only going to allow X amount of volume of fuel to be put into the cylinder. And that is how they regulate your fuel efficiency and how much fuel you burn. So if an injector is stuck open, that fuel is just going to be flooding that cylinder, and it will not run. You'll have a dead cylinder. It'll be a problem. Or if you get junk in there and the injector is stuck closed, the computer is going to tell that injector to open and close, but it's not going to be opening or closing because it's stuck shut. So you won't be feeding any fuel to that cylinder, which is a whole nother problem. But you get the concept of the longer the injector stays open, the more volume or amount of fuel you are giving to that cylinder, which is burning more fuel, giving you more RPM, etc. So as you advance the throttle, the injector pulse width is going to stay open longer. Most injectors have little tiny holes in the top of them, and then based on the model, it will have either bigger or smaller holes to feed it either more or less fuel based on the horsepower of engine that you have. And that's going to be the basic overview of an electronic fuel injection, or EFI 4-stroke, which is pretty much all the outboards that are on the market today that are 4 strokes are an EFI. Now, there are others that are going to be direct injection, mainly just Yamaha's XTO. Now the other ones are going to be an Optimax and an HPDI. So these are going to vary in how they supply fuel to the engine. So direct injection is different than fuel injection, because in fuel injection, the injector goes straight to the intake. And on the intake, it is put behind the intake valves. So you've got air coming to the engine, and that fuel is put into the air and then sucked in through a valve to the cylinder. Whereas direct injection has an injector that goes straight into the cylinder. And the fuel pressure is going to vary between a direct injection and a fuel injection. Fuel injection, usually it's somewhere around 45, 50 PSI is all the pressure that you need, whereas direct injection, it's usually a lot higher. On like an Optimax, it's around 90 to 120, and then the HPDI is going to have fuel pressure around 600, 650, somewhere around there, 700 at idle, and then at wide open throttle, it could be 1,000, 1,100, 1,200, somewhere around there. And then an XTO at idle, being the 425, Yamaha's 425, that thing is going to idle at like 1160 fuel pressure, and then wide open it could be like 2,900 to 3,200 PSI, which is astronomically high, and you cannot read that fuel pressure without a computer. They have pressure sensors built onto the engines, and without the computer, you cannot read your idle and wide open throttle high pressure, because it uses a direct injection pump or a high pressure pump outside of the VST. Now let's go over these different engines and give it a little bit of a scope on how the operation of the fuel systems work. We'll start with the Optimax first. I might be a little rusty on this, been a while since I worked on Opti, but here is how the fuel system works on the Optimax. So fuel's going to come in, it's going to go through a filter. It is then going to go to a low pressure fuel pump. Now on some of the Optis, the fuel pump is external, and some of the Optis it is internal to the VST. So, you know, we've gone over all that multiple times. And then this is where it's going to get interesting. So we understand filter, low pressure, high pressure, and regulator. But once it gets to this point here is where things are going to change, because an Optimax has a fuel injector and an air injector. And the main thing that you want to know about an Optimax is that the fuel pressure is higher than the air pressure, because it needs to squirt fuel through air, and then that is what atomizes the fuel. So the fuel is going to come out of here, and then once it gets over to the fuel rail, that is where things are going to get interesting. So we've got this. We've got the filter, low pressure, high pressure, gets to the rail. So now is where things are going to get interesting. So let me erase this, and then we're going to go based off of the fuel rails and how it operates at the fuel rails. So for an Optimax, the fuel is going to come to the rails. And there's going to be, basically think about it like there's two different rails. So there's only one, but think about it like there's two. And one will be inside the other one. So this outside is going to be fuel, and the inside is going to be air. And there's an injector here, and there's an injector here. So these are fuel injectors, and these are air injectors. So we got air injectors and fuel injectors. So the fuel is going to come to the rail, and then that fuel pressure that is here at the rail is generally going to be 90 psi. Now the fuel pressure is not going to come out of the VST like that. The fuel pressure coming out of the VST is going to be 45, somewhere around there, 50, something. You know, it's going to be a low type of pressure, but high pressure. Somewhere around 45, 50, 53, depending on the model. And then the air pressure is going to be 80 psi. But the thing that goes on here is that this pressure is all built on an air compressor. So you have an air compressor here. And that air compressor is what's going to feed air from here down to the rail. Now the rail is going to have different diaphragms in there. One is going to be a tracker valve, and the other one is going to be a pressure regulator. So the tracker valve is a valve that goes in between these two rails. It's not going to be port starboard or anything like that. You're going to get the idea of what's going on here. So right here, there's going to be a valve between these two rails, and this is going to be a tracker valve. Even though it's not really a valve, it's just a diaphragm with a spring in there. But what that does is that maintains the difference in PSI. So usually 10 PSI difference. This 10 PSI difference is what's going to be held here. So if you do not have 90 PSI and 80 PSI, that is because most of the time the tracker valve is messed up. If these are real close and you've got fuel in the air side of your air rail, then that tracker valve is most likely the problem. But there is also going to be a regulator. So, and this regulator is going to be an air regulator. So you've got an air regulator that regulates the air pressure coming from the compressor to this 80 psi. Then it is also going to have a fuel regulator. So this is what is going to make this whole system work. And you'll notice that the air compressor is regulated with this air regulator to regulate the air pressure in the air rail. The fuel pressure regulator is what regulates the fuel pressure in the fuel rail. The tracker valve makes sure that they are 10 psi off. So if you do not have air pressure from the compressor, then you're not going to have fuel pressure. So you cannot just check your fuel pressure and try and diagnose the engine based on the fuel pressure if you don't have air pressure. So you have to get the air pressure right before you can diagnose anything else on this system. But this is the heart of the whole system, being 80 psi air, 90 psi fuel, all regulated, and then a 10 psi difference built into it with the tracker valve. The fuel is going to be shot from the fuel injector in through the air injector, and then the air injector, shoots that into the cylinder. So whenever the fuel goes through the air, that atomizes the fuel and the air together, which atomizes the fuel into the cylinder. And that is why it is crucial that you have 90 psi fuel and 80 psi air, because if you have the same psi, then it will not atomize correctly because you have the same pressure. But when you have 10 psi difference, you are shooting higher pressure fuel into the air. If the air was 90 and the fuel was 80, you wouldn't be able to shoot fuel, 80 psi fuel into 90 psi air, because the pressure is going to overtake it. But this is the basic overview of an Optimax and its direct injection into the cylinders. Now obviously this might be a little bit variable. This is probably flipped. I want to say that the regulators are on the port rail and the tracker valve is on the starboard rail, but this is just for you to understand how this system works. Now let's get rid of this and talk about the HPDI and how that operates. So the HPDI is going to be the same as all the other ones. The fuel is going to come to the engine, it's going to go through a filter, and then it's going to go to the VST. So once it gets out the VST, this is where the HPDI is different. So the HPDI is going to have the VST, and outside the VST, there's going to be a filter. This filter is super important. That will cause you all kinds of problems. It's a little canister filter. They're like $100 some. So that one, it was something that people always overlook. Then this fuel is going to go to a fuel pump. This fuel pump is going to be driven by a belt that runs off of the crankcase. So belt driven. There are other filters inside of this pump. There's like 4 filters in there, I want to say. And then once it gets out of this fuel pump, it is going to go down to the rails. Where you have injectors. So this fuel pump is going to be what creates the fuel pressure that runs these. Now the thing about these injectors is they are ran off of an injector driver. So this is a pretty simple system. There's not a whole lot to it. You've got the VST, the filter, and then the fuel pump that has filters in it. Now this fuel pump, being belt driven, is going to produce around 625 psi. And then at wide open throttle, it's going to be close to 1100 psi, somewhere around there depending on the model. Some might be 900 psi. It's going to vary depending on if you got a 150 or you got a 300. Those are going to change, but it's always going to be around 625, 700, somewhere around there for your idle. As you advance the RPM, the pump spins faster, it creates more pressure. These injectors go straight into the cylinder, but they utilize what is called an injector driver. And the injector driver is basically kind of like a computer, but it does control these injectors. And so if you have a problem with the fuel pump, like if you're not getting the right amount of fuel or something like that, that is a pretty easy diagnosis, because you can check the pressure on the VST here, which is usually somewhere around 53 psi, somewhere around there, 46. The model's going to depend, but you're going to get fuel up to the filter, over to the fuel pump. The fuel pump can only be checked with a computer. You cannot put a gauge on this, so you have to have a computer to read this fuel pressure. Now, once you read that pressure, you can see it idle. As long as you're around 625, 700, somewhere around there, the miles are going to vary. But then once you watch that on a computer, if you do not have wide open throttle and you run wide open throttle and it is not producing fuel pressure, you need to rebuild this pump. They do go bad. You might have a problem with the belt. This is all mechanical type deal. But these injector drivers can give you problems, because if this little injector driver goes bad, it will mess up the way these injectors function. So other than that, it's a pretty simple system. There's not a whole lot to it. They just seem more complicated than they really are, just because you can't see this fuel pressure unless you have the computer. But when we move over to the XTO, it's a little bit different, because this again is direct injection. But let me erase this and we'll talk about the XTO, because it's a whole nother animal. So the XTO is a lot different than pretty much everything else, because it has 5 fuel pumps in the system. So same thing, the fuel comes in, goes through filter, then it goes to a low pressure fuel pump. But this is where it gets interesting, because it comes out of here and it goes through a check valve. And once it comes out that check valve, it's going to go to a T-fitting. And that T-fitting is actually going to have another like relief valve on it. Which is always going to come back to here. Now, once it has this T-fitting, it comes into the VST. So the VST is going to be different on the HPDI than it is, or I mean on the XTO than it is anything else. But this is one difference that the XTO has. Basically what it does is this check valve puts pressure through. Any excess pressure, there's a relief valve here to feed it back, just in case there's, you know, excess pressure coming from this low pressure pump for whatever reason. That's the only real difference in the XTO. As far as this system goes, they've added these relief valves and these check valves in here, because the way this system works is just, there's a lot more going on here. So once we get to this VST, let's talk about that, because this is also completely different. On our XTO's VST, it's different than everything else, because there are 2 fuel pumps in here. A sub pump and a main pump. So the sub pump only works when the engine is above, I think, 5,000 RPM, something like that. It's like from 5 to 6,000 RPM, the sub pump comes on to assist the main pump in keeping up the pressure. I want to say that the fuel pressure is like 58 PSI at idle coming out of this VST. It may be a little bit less than that. It may be like 50 or something. I think there's a range. It's like 47 to 58 or something like that as the range at idle that this system here should do. It has a fuel cooler going in it. It does not have a float, and it does not have a pressure regulator in it. And then something else that it does have is it has a fuel pressure sensor that then lets YDIS, or the computer, know what the fuel pressure is inside the VST. So that's what makes it different. Sub pump, main pump. Sub pump is from 5 to 6,000 RPM is when this will operate, just to assist the main pump. And then once the fuel comes out of this here system, we're also going to go to some more check valves and relief valves and a pressure sensor. So now let me get rid of this and go into where it goes next. So the fuel is going to come out of here. It's going to come up like this, and it's going to go to a check valve. That check valve is going to go to another T-fitting. The T-fitting is going to have another one of these relief valves. And then once it goes through this whole system, it's going to go to a sensor. So we've got the VST over to this check valve. It goes to a T-fitting through a relief valve just in case there's, you know, pressure there, up to a pressure sensor, and then from the pressure sensor it goes to a filter. And then from the filter it's going to go over to 2 fuel pumps. Now these fuel pumps are going to be driven, they're mechanical fuel pumps. They run off of the exhaust cams, I believe, and that gets us to the pumps. So we've got VST, relief valves. I'm pretty sure these check valve and relief valves are for like heat and stuff like that. So, you know, when you turn the engine off, these are used to, you know, let fuel flow to where it does not like vapor, you know, it doesn't vapor lock the fuel system or anything like that. It's heat related. Pressure sensor just for the fuel pressure after the VST, the fuel filter, and then these 2 fuel pumps, they have pressure sensors in them, and they are ran off of the exhaust camshafts. And then these will then go up to the fuel rails where you have your injectors. These injectors, just like the HPDIs, are ran off an injector driver. So that's the XTO, and like I said, it's a lot more complex. There's a lot more going on because you have, you know, there is check valve, and there's this coming in. So you've got, just so we can kind of get through here, there's 2 pumps. The fuel comes in, goes through a filter. Once it goes through the filter, it comes up to the fuel pump. The fuel pump goes through there. There's a check valve, which is there to relieve pressure if there is any. It goes to the VST. The VST does not have a float. It does not have a regulator. It does have a fuel cooler, and it does have a pressure sensor built into the VST. 2 pumps, a main pump and a sub pump. Sub pump only operates after 5,000 to 6,000 RPM. That builds pressure, comes over to here. You have more check valves, more relief valves, so that way whenever you turn the engine off, it lets, you know, heat dissipation and that kind of stuff for vapor. Then it goes to a pressure sensor, then a filter, then 2 more fuel pumps that then create the fuel pressure that have their exhaust cam driven. They go up to the injectors that are then ran by injector drivers, and that is how you get 2,900 to like 3,100 psi of fuel pressure for direct injection on you know, 425 or a 450 Yamaha. Now, direct injection again is basically, it's injecting the fuel straight into the cylinder, and it is not directing it behind a valve, whereas EFI, electronic fuel injection, is going behind a valve before it gets into the cylinder. And so that is how pretty much all Outboard's fuel delivery systems operate. Depending on the model, it will have some variants of these types of systems for it to feed fuel to the engine for the engine to run. Now, anything I missed, let me know in the comments below, and let me know what you think.